Okay, welcome to our last lesson on differential equations. This one, 8.3, about population growth models. And we've got two objectives here. First one, to use differential equations to model growth and decay in applied problems. And this is common to both the AB course and the BC course. It is stuff that you did in pre-calculus, actually, pre-cal and algebra 2. But now we're going to see the calculus behind how that exponential growth and decay equation comes about. And the second objective is BC only topic, to solve and analyze logistic differential equations. And with that objective, if you take a look over here at the assignment, you can see that there is a very, very morbid homework supplement. You'll see what I mean whenever you check it out. Okay. So looking at our warm-up question here, the variable y is directly proportional to x such that y is equal to 12 when x equals 15. Write an equation that relates x and y and tell me what is the constant of proportionality. So yeah, this doesn't look like a calculus problem. It looks pretty much like an algebra problem. But we're going to use this as a jumping off point, and you'll see the significance of it in a bit. Okay, so when we're talking about direct proportionality, that's what we're talking about here. Our equation, if you remember from algebra, looks like this. Y is equal to k times x. And this k that's right here, maybe I change that color again. This k is our constant of proportionality, what this thing is talking about. Right? So I'll start off with that general equation, y is equal to k times x, and then I'm just going to plug in the condition that they gave us, that y is equal to 12 when x is equal to 15. So I've got 12 is equal to 15 times k, and then I solve that for k by dividing. I get 12 over 15, which has a common factor of 3. So I get a k is equal to 4 over 5. So this 4 over 5, that is my constant of proportionality. All right, so far so good. And then it is asking us what is that equation that relates x and y, so we'll just rewrite the equation with the constant of proportionality thrown in it, and we have y is equal to 4/5 times x. I know what you're thinking. What the heck does this have to do with what we are talking about in this population growth model lesson? Well, we'll see. Okay, so first objective, it's about applying differential equations to growth models and decay in applied problems. And specifically, this is just generally unchecked exponential growth. And you probably remember from your prior math classes what that exponential growth equation looks like. It's used both in biology, chemistry, and in finance for compound interest, continuously compound interest. It's the same exact equation. So mathematical models, they often take the form of differential equations for the simple reason that stuff that we're measuring changes over time. Like, for example, populations. Usually those things change over time, so we use differential equations to model that kind of situation. Okay, so here's our kind of general assumption for these population growth models. It's not unreasonable to assume that the rate at which some population increases is directly proportional to its current population. Well, at least under ideal situations. And what that means is that you don't have to worry about limited resources and limited space. So under some ideal conditions, it's not unreasonable to assume that your population growth rate is proportional to the population. And what that means is, essentially, as the individuals in your population reproduce, well, you have more people in that population to reproduce, right? So your population just gets bigger and bigger and bigger. And what populations are we talking about? Maybe they're bacteria, maybe they're bugs, maybe they're bears. Okay, so this is called the law of natural growth, and it arises From this arises our exponential growth equation, as we're about to see right here. So based on this assumption, here's our differential equation that we can get from it. So we have that dp dt is equal to k times p. This looks just like that direct proportionality question that we warmed up with. So here we've got our population. And the dp dt is the rate at which that population is changing, growing, shrinking, whatever. And then finally, our p here is our constant proportionality. We're saying that our population growth is directly proportional to the population at any given time. Okay, so now I want to solve this differential equation. And the first step that I do in solving differential equations is to separate the variables. So I got to get the p over there to the right-hand side, this p for this population, get it over to the left side, I should say. And the dt belongs over on the right-hand side. And we keep the k over there with the dt just because it's going to be easier to integrate that way. And then I take the integral of both sides of this thing. You're going to see some math happens, and then we get p is equal to c times e to the kt power. You may remember this in another class as the PERT model, right? So what we're calling this law of natural growth is our exponential growth equation. So what I am going to do is in the next video show you the math that's actually missing in here, that purple arrow, show you all the math that's involved in deriving that exponential growth equation.